Physics chapter 25 theory video 3, the charge to mass ratio of an electron. Um, uh, so now we have done, we know that electron is a very tiny packet of energy. So to find the ratio or charge to mass ratio of an electron, that is E upon me. This is going to be the specific charge on an electron. That means the per unit mass, that is the charge of an electron per unit mass. We need it because we need to figure out how much of energy is transferred from one place to another. So these are all interconnected and are quite useful in our fields of studies. Now, using an electron that is traveling in a circle in a magnetic field, we can obtain that E upon me is going to be V upon Br. Therefore, we can obtain a relationship by using V, B, and R to figure out the mass to charge to mass ratio of an electron. It is not easy to measure any of these measurements because we can't actually, even R is not going to be easy because of parallax error. There are many measurements, there are many methods that scientists have developed to figure out how to do this right without minimizing the errors. Now, one way that we can do is using the potential difference VCA between the cathode and the anode. That is, between the cathode and the anode, we use the potential difference. This would allow each electron to accelerate when it goes from cathode to the anode. Because a single electron has a charge of negative E, then we know that the work done is going to be E into VCA. So this work done is going to be equal to the kinetic energy of an electron when it leaves the anode. So at the cathode we can assume that it has zero kinetic energy. Therefore we can take it to be EVCA equals half MeV squared. Me is the mass of the electron and V is going to be the final speed of the electron at the anode. So then we can remove V from the equation. Then we get EVCA equals half MEV squared. So that means, which is going to be equal to R equals MEV upon BE. So this relationship E equals ME equals 2VCA, because you cross multiply 2VCA divided by R squared B squared would be the final equivalent for mass to charge ratio. E equals ME, E upon ME. So this allows and it allowed scientists to figure out the mass Me of an electron. This might sound a little bit difficult, but it is not actually. The only thing that you need to remember here is that the relationship between the kinetic energy and the potential energy that is generated as a result of this particle moving through a magnetic field. If you do not understand, or if you need a revision on how potential difference results in these things from happening, please raise questions, then I will give you answers for those. Before we move to the worked example, let's write down a note. The charge to mass ratio of an electron, within brackets, E upon me, E upon me, E upon me can be defined as specific charge on an electron, within brackets, per unit mass. From above, that is from our earlier video, considering an electron traveling in a circle in a magnetic field, we have the relationship E upon me, that is the mass of an electron, E upon me equals V upon Br. Because direct measurement of these values are difficult, we reach this using different other methods. Leave a line and write. One way is to use the PD between cathode and anode, VCA, which causes each electron to accelerate towards the anode. Considering that each electron has zero kinetic energy at the cathode, we can say that the work done would be equal to the kinetic energy of the electron as it leaves the anode. Then we can take, therefore, EVCA equals half MEV squared, half MEV squared. ME is the mass of an electron, V is the final speed of the electron. Simple V is the final speed of the electron. Here you have to remember the capital V stands for the potential difference between cathode and the anode. So we can get rid of V from these equations and obtain E upon ME equals 2VCA, capital V, 2VCA divided by R squared B squared, R squared B squared. Right, now let's go through this worked example to understand better how scientists use different methods to figure out how to find these values. You are going to get calculations, not too much of theory out of this part. So you should know how to use the equations, and you need to have the equations by heart. An electron is traveling at right angles to a uniform magnetic field of flux density 1.2 mt. The speed of the electron is 8 into 10 to the power 6, 8 into 10 to the power 6 meters per second. Calculate the radius of circle described by this electron. E equals 1.60 into 10 to the power minus 19, minus 19 coulombs, and Me equals 9.11 into 10 to the power minus 31 kilograms. So those details have been given. So the first thing is we have to use the magnetic force on the electron using F equals BeV. So you need to know this equation by heart. Then you have F equals 1.536 into 10 to the power minus 15 newtons. So why do we need to find the force? Obviously because without the force we cannot find the radius. The question they are asking is the radius. So F equals MeV squared upon R. So when you substitute the values that they have given us, we can obtain R to be equal to 3.8 into 10 to the power minus 2 meters. Then if you use the equation R equals MeV divided by Be, you would still get the same answer. So I would suggest that you do question number 4, 5 and 6 to get a better understanding of this, and then after that we can move on to the next practical activity. If you have any further questions, please raise them.